Right. Got it. Share my screen. All right, you're good. Okay. System control. What does it mean to control a system? Like when we say you're controlling a system, what do we mean? Think about it for 30 seconds. $15 more seconds. Those of you that didn't take control, what do you think?
You're dealing with inputs and outputs of a mechanical system and reading that in order to get some sort of, whether that's a physical movement or some sort of, electrical output, you're able to do something based on the.
No. Very scientifically, no. Very scientific, but no. What you explained was a system. Input-output system. We have done systems so far, right? We modeled them, the kinematic, the dynamic. James, have you taken control? So I said those that they did not have, because you should know. If you don't know, we have a problem.
The algorithm, like order of operation, logic behind all what you mentioned.
So, not cigar. Who haven't taken control? Just raise your hand. Be great. Okay. Well, no, someone else. Right there. Yes, you. No. Sorry, I forgot your name. Yes. Yes.
What was the
Control system. Who drives? Who has cruise control in your car? Now, now those of you that didn't have, what does your cruise control do? The thought process, right? Like conceptual question I asked, I always talk about that, but like most of us is not important concept. All right, someone that didn't take control and drives a car that has cruise control. Tell me what you think controlling the system. Max.
Maintain the speed that is set.
So in cruise control, the cruise control maintains the speed that you set, right? So what are you doing? You're manipulating the speed of the vehicle, right? By some means.
manipulating variable?
So you're manipulating some variable in the system input, right? To get what? A desired output, which could be the velocity of the car. Speed, not velocity, it doesn't go backwards. Speed of the car, right? That is technically correct. Otherwise, someone will point it at you. So, we usually, when we say controlling a system, we are manipulating some input in the system, right? To get to a desired performance or an output, right? So in your cruise control, you don't know what's happening in the algorithm and the code, right? You just press a button when you're at a certain speed and it holds it there. All right, then what's the next thing you do? Imagine you're driving, right? So me, 79, and then put the on 55. Pressing the button, right? Then what's the next thing you think I'll do like automatically? Take my foot off. Why? I don't have to manipulate that. That's the input, right? The angle of the gas pedal is the input that does something that results in the speed of the car going up and down. Injecting more fuel to the chamber, more gas, you'll turn faster and then the speed, right? So when you set the amount of gas going into injecting gas into the chamber, then you're going to get the same speed. It's going to stay there until like try, imagine that you're going on a flat road and then you climb a hill. What happens even when you have the cruise control?
Pretty sure, yeah, and it has to.
But you're not changing anything. It's on cruise control. You're not touching anything. What do you observe by looking at the speedometer? Slows down, falls back a little bit, and then catches up. If you're driving an older car, you hear right? Get back up to speed. Because the car is trying, the motor is trying hard to get back to that desired speed, desired output. So that is control. You're welcome. That's all. Yeah, that's it. Now let's see if we can plot that, graph it, right? So everybody now gets what the concept is, right? So I'm using the cruise control. I'm giving you that example, but then I expect you to understand other system, right? When I say change the input, you know what the output look like. So that's the reason for the example. So cruise control, you start from time 0, right? The change of the speed happens in time domain, right? So I'm going to have a representation of time domain because I want to plot and show what's actually happening. I'm going to explain to someone what's happening when we have a controller. And then we can decide if it's a good controller or a bad controller. So if my x-axis or this axis is time, I'm trying to manipulate the output that's called the speed. What's my vertical axis or y-axis? I'm not that boring. He's yawning at me. Speed, right? We like to show them functions of what? Speed is function of what? Time, v of t, right? So how do you see the speed of your car? You have the speedometer, right? So something is measuring it and then puts it in the display, correct? So this is usually what is being measured. We also call them y, like not y. We usually call the measurement y of t, and we are in time domain. All right, now y of t could be different things. Could be the position, velocity, temperature, pressure, whatever you want, whatever you're trying to manipulate for the desired values. Now, let's say that you are a good citizen and a good driver, and you're studying 65 at 65. miles per hour. Well, I have to convert it to time. So time is hour here, it's not seconds, right? So I'll be technically correct. All right. So what happens? So what is that 65? Is your desired value, right? What do you want to have? Do you want that to change over time or be fixed? Fixed, right? So I like to see this over time. At 65, nothing happens. If anything happened, I want it to go back to 65. So that's my desired value. Now, what does happen in reality? So let's say I start at time 0, right? I'm at, well, my speed is 0. What happens, let's say after 5 seconds? You get some speed, depending on what you drive, right? Because if you drive a Porsche, you could be already at 6. Right? I don't know if it's 3 seconds, I don't know what's the number, but. No, you don't cruise control. Cruise control is to set the desire. You have to actually use the pedal to go up, then set it. Right? So let's say you're gonna be here, and then at 10 seconds, gonna be here. And then at some point, you're gonna reach to the value we wanted, right? And then you said, and that's what you want to stop there. That's where you press the cruise control. So you're doing something like that, right? So this is the response of your system to the input you give to it and whatever the computer is doing. How fast the fuel is being injected, how strong the motor is, right? How good it is the wheel and axle, what is it called? Huh? is icy, but I'm talking about like,
We're talking the engine or?
yeah, well, from the engine to the wheel.
Differential.
Right? Even if all the goals, this time may change, right? Now, this is one car. This is your car, just. This is my car. This is my husband's car. Ford GT. Excellent. All right. Oh, he did not hear me. Okay, so what's the difference? Which one is better? Could be. Is there any other, like, any objection to what he said? How's it fine? Because he has to change his tires a lot faster than I do. Right, because you rev faster, for example. So when you are defining what is better in and that you're controlling, you have to define what better means. Does faster mean better? For some application, yes. Right? Sometimes better is how much energy does it consume. Up to here, I'm fine. Behind faster than this, I have to spend more money. That beats the purpose. I don't want that. So this is not necessarily a better system, better control behavior, right? Depending on what you want. So every time we talk about control, you have to first define what is a system, what is it that you're controlling, like what is the system? What is it you're controlling in that system? And what is your desired behavior that you want? Because at the end of the day, you always have a control law. You're going to manipulate some coefficients, let's say subtract the PID controller, the simplest one, right? Change the key controller. You can bring this line really close to vertical, but then when you're designing, then you have to go buy the thing to build it. Then you say, oh, I have to buy $5,000 motor. This has to react this fast, which if it was slightly so 1 second slower, I would spend $500. For my application, that's good enough. 1 second doesn't matter. But depending on the application, depending on how you want the performance to be, you will choose what behavior is good. Right? Now, imagine you have a system, some time is in time domain, some measurement, some desire, some output, right? You have some desired value, whatever that is, Y desired. Then this is the behavior of your system. Is that good? Why is it not good? Why is it not good? Why is this is not good? So why oscillation is bad? So well, this is a stable because it finally reaches to a steady state. Technically it is, but over this time, what happens is whatever is the output is keep changing. So imagine you're driving, like when you just learn how to drive and try to stay at 60 and keep from 45, 67, go back to 35, go back. The next the person next is 50. Right? Bad system performance. At the end of the day, after 10 minutes, you're like, I'm at 65. Right? So really depending on the system, the performance, the requirement, you will look and decide if this is a good thing. Sometimes you'll see that I'm explaining all of this here because these are the behavior of the system. The thing is in control, you're gonna have plots like this and you're gonna look at it. Yeah, that looks good. And that becomes, yeah, this is the controller behavior that you like. So you have to tune the coefficient and you have to observe the behavior and decide if this is a good fit. Now, it's not all just observation, we measure things too, so we will have, okay, how much time it gets for it to peak first, how much time it gets for it to settle. But before we get to all of those nitty gritty, we can just look at it. Now, if it looks like this, so you're supposed to be here, but your system does something like that. Depending on the system, this could be acceptable. There are usually thresholds. You usually ask, okay, what is it that you want? You know, this is engineering. There's always trade-off. So maybe having this peak is okay if we settle down after 50%, right? So all of these become. So we kind of are deviating from, there's a formula, this is your robot, apply and model. Every engineer designed their controller very differently. No two engineers design the same, come up with the same coefficient for the controller. The behaviors look alike, the numbers vary. It's very unique how you choose your controller, how you calculate this. All right. Okay. We're just getting started. Great. All right. So a typical control system for a robot could look like this. Am I not? Ah, no, I wanted to go to full screen. Full screen. I was in full screen. All right. So a typical robot control looks like that. You're gonna have some desired behaviors, all right, that goes to our controller. Controller is a box that usually we have digital control and analog control, right? So you can either code it or you can put the component and then build a controller in your system. After the control, you usually have amplifier to amplify the thing that you want, the output. It goes to your actuator, things that move, right? Most of these actuators, they have their own driver and controller inside, and I'll tell you why in a bit. Then those actuators have torque or forces, which are, if you remember from dynamic, was the external forces of your dynamic system, right? It goes to your dynamic system, and then you got dynamic equation. So you had the system, you modeled it, came up with two equation for your like to our system, right? So it goes into that, solves it, and looks at the output you wanted. Let's say theta dot, which is the velocity, right? And we read that theta dot through some sensors, right? Let's say spectrometer for velocity, and we will compare it with the desired value. If it was the same, you're good. You're gonna hold everything where it was. If it's not, then the controller is gonna manipulate and change the values, change the input to the actuator to bring that output that we desire to the value set. Now, that looks complicated because it has so many components. A simplified model and version that people work with at the beginning to come up with our control law is this kind of model, then we add more components to it. So we will have desired value, we have our controller, we have our dynamic. Let's say that, okay, let's assume this controller directly controls the system, right? The tool. So we are eliminating the actuator, amplifier, everything. Measure and see what you see. So it's so we are making a lot of assumptions, right? So this is not what the reality would look like. It would be a good base for the actual system. Then we do our experiments and then measure and say, okay, now, what do you think are in these boxes? So technically, there is like this summation points here that I didn't show, but it's inside the controller that checks the difference between them. So what are in these boxes? Because you're just representing, right? When you should code something, you need something in that box. Yes. So we could have different ways of doing it. One is transfer functions, right? There's an S domain. You could do it in time domain. You don't necessarily control in frequency domain. Transfer function and then convert it to frequency. So because we experience life in time domain, it's easy for us to say everything in time, but then for frequency, we don't experience it. So they define in like an intermediate phase, it's called estimate, Laplace. Laplace has a direct relationship to time and frequency, right? Then we go from there. So you either see transfer functions here, or if you take steady state control, then you actually see the steady state version of the distribution. All right. Now, if you're ECE, you had 2020. You know what transfer functions are. Like I'm just asking what they are. If you're mechanical or other subjects, aero, have you seen transfer functions? Yes, okay, in some courses, right, before that. Right. Because control used to be the prerequisite for this, so I didn't have to do all of that. But I always check and make sure everybody knows. All right. So I already kind of talked about it, but here's the thing. We always write our system like this. This is block diagram. We will find what our system is, what's the controller, what does our sensors look like. Now, here's one thing. When you read the data back through something, through sensor, let's say, right? You have to read it through something. And it goes back to your control to check and verify if that's your desired. If you're deducting that, you're comparing, this becomes a feedback loop, or feedback. I'm gonna put in parentheses controller, but this is a feedback loop. So this is a negative feedback because we could have positive feedback. If you change singly just the sign, a very stable system becomes a very unstable system because you're adding the error to the system, right? Instead of deducting and then finding like how to fix the system. So that is very important, making sure that's negative. All right, so hence this is also negative. So every time we talk about feedback control, we mean negative feedback. So if they didn't tell you what kind of feedback control you have, default is negative. If you're coding in MATLAB, the default is, all right? So error is desired, well, it's your actual value minus desired. Where do you read actual? Here. Actual value is what comes from your system. Desired is what you set. Now, you see that in the simplified version, instead of the box for sensor, we removed it. What does that mean? Can we just remove things like in the system? We're accuracy, right? What are we saying? So from signal and system, if this has a value, let's say YA, and this is a block diagram, let's say this is A, like the gain is A. So you have Y0 come from here. What do you see in here? So that signal is going through a block with the gain of A. What comes out of it? A times Y0, right? If this was Y0, what would be here? Y0. What if I said the gain was 1? Right? So we didn't just take that block, we said that it's going to be a perfect sensor. It's going to exactly measure all of our output. Because all the sensor you use, depending on the resolution, they will lose a little bit of the actual picture, right? But we are thinking about what if we had the perfect sensor? So we're getting all, so we're designing a system for a perfect situation that we model here, right? So the error still will be this, knowing that we thought it's a perfect measurement. You will need this information to do your checkpoint. So that's why I'm staying here so long. We have 3 types of problems when we deal with systems. One is that when we deal with control, sometimes you have the input, you have the output, you don't have the system. You have to model that. Output over input is what? Transfer function. That's the definition of transfer. So that's system identification problem, right? What is my system? You can do black box, all those methods. Sometimes you have the input, you have the system, you have the underwater robot, you know that you can control the thrusters, you want to know what happens to it. Then you set the thruster velocity for something on RPM. That problem is your kind of simulation problem. You're not going to set your device for 100 velocity, what happens. You just run simulation. So if you have the input, you know what your system is, you have the formula for the model for it, you can just use simulation to see the performance, right? Now, some problems, you have a desired output. You have the model of your system, you want to know what kind of input will produce that kind of output. That is control problem. Now, the thing is, you never get a direct control problem. You first have to model your system, which we already did. Then you'll have to do simulation, which you already did. Then it's like, okay, now I need to figure out what input creates that output I've seen. That is control problem. You have to constantly go through this loop. Sometimes you have to adjust your model because you estimated everything, right? So sometimes you have to understand what kind of input gives you a certain kind of output. So this is the process as a control engineer, as a roboticist. This is the process that you have to go through. Knowing that you already figured out the modeling of the system, and you know how to simulate it. All right. So I already talked about all of this on the title slide. So these are for you to review afterwards. Now, we have two kind of control loop. Let's call it. We call it the loop because you could have a big system like a car, but you could have a smaller subsystem that you're trying to control, right? Controlling the light of a car to turn on and off during night, the control loop, right? It's part of the car, but it's in the subsystem. So we could have open loop system and closed loop system, open loop control and closed loop control. Sometimes you don't need to read the feedback to control something. We call them open. So open loop control exists, and for some certain application is valid. Sometimes you need to have a feedback to be able to control. Can someone bring an example of an open loop system, open loop control that is valid?
Sure.
Servo is a system, what are we controlling?
The actuation.
What is it that you want to do? So when you say desired, and then you start rotating, you need to check. As soon as I need to check if it is desired, then you're in the feedback loop. Okay, think about your everyday life. Someone other than Max has been answering all my questions, and he has experience. So someone else, think about breakfast. Sunday control for it. Okay, let's go back to life. Change. Toaster. All right. So what does toaster do? You put the bread in, you put your number, it toasts. You grab it. With experience, you know, number 4 in my toaster is like really dark. Number 4 and yours is perfect golden, right? So that is an open, or think about the water system, like when you were watering the glass. Turn it on, water for an hour, I come back, turn off. You don't measure the wetness of the soil in a normal everyday life, not just right? Things that you don't need to look at the result and manipulate again, those are open loop and it's fine to have open loop. Now, you said up loop, Rocket?
Yes.
Okay, so tell me about the performance that is open loop.
It's not like it's a bottle rocket.
Oh, bottom rocket. Okay, sorry. I get wrong. Yes. Yes, you don't care, you just want to see it go. I'm sorry, it was my bad. I didn't hear you very well. Or let's say you're drawing your clothes, right? You set it to some number, it has some like scale and base, okay, this is 10 kilogram needs like 1 hour, you go, sometimes dry, sometimes not. The only way to fix it is rerun it, right? The machine does not constantly check the clothes and see how dry it is to go. So that's an open loop system, all right? So sometimes in our system, having an open loop is fun, sometimes not, like cruise control. You need to check, really, did I get to 65 or what I wanted? So for open loop system, you have some desired input, some desired value. Bread be toasted, right? Your controller in your toaster is what? Your timer. When it goes off, everything shuts down, right? So it's a timer. You go into your actuator, which there is the element that has heat, the heating element, does something to your system, right? Heats up, and then you get your bread out. Is it the color you wanted? Well, I didn't constantly check, bring it out. So if you didn't, if it's not, you put it through this process again, right? Now, for that system up there, we have a battery, we have that we can control the speed, it's moving it through different resistance. We have DC amplifier and we have our DC motor that rotates a disc. Now, if we wanted to draw that in block diagram, because we're going to control this thing, right? That's our system, this is our block diagram. This is our desired speed, goes to a controller, controller will move our actuator, and the actuator does the rotating thing on the disc. You measure to see how fast it's going. If it's an open loop, you don't take anything back. You don't care about the error. You just want it to move like the car. You just want it to go. But if you needed to check, if you got to your desired, you have to close the loop. So you have to get a feedback, a reading from your rotating disc. So if you connect the tachometer here, you can read the speed and then check the difference. That's how you close the loop, and we see the error here. Now, if any of these had gain or let's say transfer function, all you do, these are all signals, right? They have values. They will get multiplied, and then here you're reading multiplied, deducted from desired, you find your error. So if I ask you what's the error, and I give you values for input, output, and what are each blocks, you should be able to write the signal going through from one side and coming out the other side. Signal and system 2050, for instance, right? That's what it is. And I'm sure that ME's and Aero has something similar to that. Yes? So this is our open loop. This is our closed loop. This is important. I'm going to talk about this afterward, but I'm going to solve this. We are going to calculate the error of our control loop that we just saw. Okay? Well, part of it. So now in here, you have R, your input. You have a controller, the gain 1/10, that goes into this open loop, which has, this is our plane, what's happening inside the plane. You have an omega, usually a noise, something comes from the environment, goes into some box to the gain of 0.5, and then gets deducted from the input to the system, multiplied by 10 becomes your output. Now we want to calculate what's the error of this system. Well, what we want to calculate the error of the open loop system. We still can calculate the error, but you're not taking any action, right? We want to know if the input R is R, after all of those that happen, and the output is Y, what is the difference? So take a few minutes, try to write this. Try to find that. A good way of thinking it is that your final solution will have your input in it, R. So you want to write this part. So I'm gonna write this one. U is R times 1/10. This is R over 10. So this is R over 10. This OL means open loop. This is your noise. This is YOM. This is going to be R minus Y open loop. I believe everyone is on the right track. So here are things that happens. This is 0.5 omega. This one is R over 10, gets deducted and multiplies by 10. So U from here minus 0.5 omega times 10. U is also R over 10 minus omega divided by 2 or W divided by 2 times 10. So this is R minus 5W, right? So that's your output. So R minus 5W is R. Well, those two cancel out. So error of open loop is depending on what? Your noise. So for this system, the error depends on noise, right? So the more noise you get from the environment, then the higher the error of this, the difference between your input and output. Now, since this is something that the environment is impacting you, you want to control, you want to reduce it, right? You want to make sure that your Y output is close to right desired. So you're going to close the loop and then calculate what is there. That's your system. You do the same thing and you'll over there, you'll have W showing up and you can compare how the controller impacted the output and is a function of noise, so you can compare it. All right. So back to here. So I just wanted to close that loop so you know what your checkpoint is for today. The great mass spring damper model. Why this is such a wonderful model? Other than the creative, I love it, but why have you seen every time someone talks about modeling, they use mass spring damper? What? Nathan, this time you can. You see inertia there, right? You see the restoring forces, you see damper, which is the base of energy, like friction. So you can model a lot of things that happen based on this. So when we get to designing controller for our room platform, we're going to model based on this. Because we can easily model everything in our robot in one of these elements. Something that restores energy, something that wastes energy, and something that's connected to inertia. And this is a second order system, and I'm sure all of you know how the response of the system looks like. That's the beauty, that's why we're using this. Because we already know the response of the system is gonna look like this. Right? So it can be more oscillation, less oscillation, or the case that I showed, and it's like a perfect, the desired behavior that you want. Now, do you remember in about 2020 for sure, or your other courses, you had a higher order system, and then you had to do change of variable to make it a second order? You had the system of second orders. We do that because we already know the response, so we simplify the problem to something we know how it behaves. Then we can make decisions and then bring it back to where it was. So we are making it simpler by making it look like something, you know. So in our robotic application, we are going to use massive strain dampener because we know how it's going to behave. We know the desired behavior, let's say. Then based on that, we will define those coefficients for them. All right. Just to move.
I don't know why it's not moving. But you can guess. So this is the spring, this is the weight, the mass, this is the damper. As this goes back and forth, if you track the position of this mass, it goes on that weight until it settles. In what case it does not settle? Is there a case that it will not settle?
Without friction.
Hmm?
Neglecting friction.
Neglecting what?
Friction.
Oh, friction.
You had it like upright and you got rid of the spring and just keep going.
Well, friction is. Just say something. What do you think about it?
You added, like, put a force on it that just kept increasing.
So let's say you push, right? And that starts moving. Do you think it will settle at some point or will keep going? Nobody said depends. I like kind of dependent. If it goes to natural frequency, it's gonna be there. It's gonna explode. Or depending on friction. Well, this is like wasting energy, right? So eventually, at some point, it is supposed to damp down, but it might take so long that for you, it would be unstable. So it will look like this. It could look like this. Yeah, I'm just gonna show the envelope of the response. Can go forever. Very small, minuscule change. So it's bounded, but it's not as stable. It's between two, right? So yes, there shouldn't be friction on the surface because additional friction there, right? But it also depends on the strain coefficient, right? So some systems in their nature, they could be an unstable system. You cannot control it. So you have, that's why first, when we define a system, you remember step response? Yes, because step response is basically, this is my system. I want to know if I apply force to it, the value of 1 or a fixed value, what happens to the system? So you can see the natural response of the system. Then you can see if you can control it or not. Because some systems are in nature uncontrollable. All right. This is a reminder, you probably have seen this. If you haven't, we'll get back to this at some point because we're running kind of out of time. But think this is, you've seen this. I draw this on the first page, right? When I was drawing, I was showing you the response of a second order system. The response would look like this. Now, so imagine this is a deviation, and you grab that point on Y max and bring it down. You're going to see changes here. So wherever is your desired form, you're going to stop and then look at all your coefficients like this is my controller, right? So the Y max is very important because you're overshoot. How fast you're getting to that Y max is important. 98% of your final desired value is very important because after that you can say, okay, I'm good. As long as I'm in 2% plus minus my final value, you're good. That time, settling time, that is really important. So do you remember that I told you there are some values you can calculate to say if your system behavior matches your requirement? These are those values. But again, by looking at and observing the response, you could also say that this looks like something I desire. Then let's take a quick, detailed look and see what the numbers reflect. Let's crunch the numbers. Right.
You already did this. I'll talk about this on Monday. Yeah, I'll talk about that on Monday. You can solve your checkpoints though. There's a slide.